Okay, welcome back. Let's get into this.
Yeah, let's do it.
So we've got these interesting source notes here about using calculus.
Right, specifically for optimizing crop yield. Sounds a bit abstract, maybe.
A little, yeah, but the core idea is pretty practical. Imagine you're planting something, say, corn, in a fixed area, like 1 square meter.
Okay, limited space.
Exactly. How many seeds do you plant? That's the question.
Because too few seems wasteful.
Right, you're not using the space efficiently. But then, if you pack too many in,
They compete, right, for light, water, nutrients.
precisely, they can crowd each other out, and maybe none of them do very well. So there's got to be a sweet spot.
Absolutely. That's what these notes explore, finding that optimal planting density using calculus to maximize the yield you get from that 1 square meter.
So the mission here for us and for you listening is really to see how mathematical tools, specifically differentiation, can tackle these real-world problems.
Exactly. Making that connection between the math class and, practical outcomes.
So it's not just theory then. This is genuinely useful on, say, a farm.
Oh, definitely.
Yeah.
Think about the process. You add more plants to your square meter.
Uh-huh.
Initially, more plants mean more total produce. Your yield goes up.
Makes sense.
But keep adding more, and that competition factor kicks in harder.
Right, the crowding.
Yeah. Each plant might produce less because it's stressed. So even though you have more plants, the total yield from that square meter can actually start to go down after a certain point.
Ah, okay, so the yield goes up, hits a kind of peak,
Exactly, a maximum.
and then it starts to fall off if you keep increasing density.
Precisely. And if you can describe that relationship, the number of plants versus the total yield with a mathematical function,
Then calculus can find that peak for you.
that's the power of it.
Yeah.
Differentiation, specifically.
Okay, let's connect those dots. For anyone studying derivatives right now, the derivative tells you the slope, right? The rate of change.
Correct. So when adding more plants increases the yield, the function is going uphill.
Positive slope. Positive derivative.
You got it. And when you've gone past that optimal density, and adding more plants actually hurts the total yield.
The function's going downhill. Negative slope.
Negative derivative, yeah.
So, wait. The peak itself, that sweet spot, that maximum yield, that must be where the slope is momentarily flat just before it tips over.
Exactly. Right at the very top, the rate of change is 0. The derivative is 0.
Ah, so finding where the derivative of your yield function equals 0 tells you the density for maximum yield.
That's the key mathematical insight. Find where the derivative is 0, solve for the density.
Okay, but hang on. Where does this magical yield function actually come from? That seems like the tricky part in the real world.
Good question. It's not magic, it's data. Our notes touch on this too.
Right, you can't just guess the equation.
No, you need to run experiments. Plant test plots with different densities, maybe 5 plants per square meter here, 10 there, 15 over there.
And carefully measure the yield you get from each plot.
Exactly. Collect data points.
Hmm?
This density gives this yield, that density gives that yield.
So you end up with a set of measurements.
Yeah. Correct. And then you use statistical methods, curve fitting, basically, to find a mathematical function that best represents that data. That becomes your model.
Your yield function model.
Yes. And then you apply the calculus to that model. Take the derivative, set it to 0, solve.
Wow. So it connects observation, data analysis, and calculus to get a practical answer.
It really does. It turns this sort of abstract mathematical concept into a concrete tool for optimization. You're not just finding X, you're finding the best number of seeds to plant.
That's pretty powerful. It takes the guesswork out.
It provides a systematic approach.
So wrapping this up, what's the main takeaway for, someone listening?
Well, I think it shows that calculus, especially understanding derivatives, isn't just abstract theory. It's a tool for finding optimal points, maximums, or minimums in real situations.
Like maximizing yield here.
Right. But the same fundamental idea applies way beyond farming.
Like minimizing costs in manufacturing or maximizing profit in a business model.
Exactly. Or finding the most efficient route or the optimal dose of a medicine. Anytime you can model a relationship where something peaks or bottoms out.
So the core concept is using the rate of change to find those critical points.
Precisely. It's a really versatile mathematical tool.
Yeah.
So a thought to leave you with. Think about other systems or processes around you. Where else might you see this kind of optimization problem where finding a peak or a valley using the rate of change could provide a valuable answer?
I'm an icon, man. And my girl about a 10. I should fuck her in the Benz.